have, yes. So I think I have recording going. So I just wanted to talk through a couple more examples. We've been talking about induction. We've also been talking about recurrences. So if you recall, a recurrence is like a recurrence is just a formula to go and write the term in a sequence. So you write the value of a function or a term in a sequence in terms of other values in the same sequence. So the Fibonacci numbers start with 1, 1, and then after 1 and 1, every new Fibonacci number is equal to the sum of the previous two Fibonacci numbers. So 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, right? This formula says add up two terms together and you get the next one. So if you take n minus 1 and n minus 2 and add them together, you get n, which is the next term in the sequence. So this is, a term is the sum of the two previous terms. So with that in mind, the final term or the next term in the sequence is going to be 13 plus 21, which is 34. If you look here, the Fibonacci numbers get big pretty fast. We're already like almost at 100. Yeah, I think, yes, almost at 100. So I have a claim. I claim that the nth Fibonacci, let's see, I'm going to claim to you that for n is greater than,
Hey.
oh, I'm sorry?
Do you mean to be presenting right now?
Oh, crap. Thank you so much for interrupting me. Yes, I did not hit the present button. Okay. Thank you for getting my attention. Yes, so I am now, do you see the presentation now?
Yeah.
Okay. I apologize for that. Yes. So this is the formula for the Fibonacci numbers. I will give you a moment to look at it. And yeah, the nth Fibonacci number is the sum of the previous two Fibonacci numbers. A recurrence is just a formula that tells you how to get the output of a function or a term in a sequence in terms of other terms in that sequence. And so, yeah, so basically if you add two Fibonacci numbers, you get the next one. You add two Fibonacci numbers, you get the next one. So then at the end here, if we take like 21 and 34, 21 and 34 is 55. Excellent. So this is like F1, F2, this is F3, F4, and F5. So one thing that's interesting here is that, so at 5, the fifth Fibonacci number is 5. But then after this point, so the beginning you have 1, 1, 2, 3, 5. But after this point, the Fibonacci numbers start growing really, really fast. And so here you have F6 is 8, F7 is 13. And so they just keep getting bigger and bigger and bigger. So I'm going to claim that when you're greater than 5, so for n greater than 5, f of n is bigger than n. So this is probably like a very believable claim, I hope, that the Fibonacci numbers are like getting bigger and bigger and bigger. And so like the nth Fibonacci number is bigger than n is probably a claim that seems pretty reasonable if you write out this formula. But like there's infinitely many n. Like, how do I know that the 1000th Fibonacci number is bigger than 1000, or that the millionth Fibonacci number is bigger than a million? So this is where we would use induction to go and prove this claim. So prove with induction. And if I prove this with induction, my base case is for n equals 6. So 6 is the first number that's bigger than 5. And the reason that I'm starting at 5 is because it's not true that the third Fibonacci number is greater than 3, right? The third Fibonacci number is 2. It's actually not greater than 3. But after we get out of this like weirdness at the beginning of the sequence, at that point, the Fibonacci numbers seem to be growing pretty fast. And so I'm going to start working at 6 and prove that starting at 6 and after 6 for all of the infinitely many numbers beyond 6, that the nth Fibonacci number is bigger than n. So f of 6 is equal to 8, because I went and did it right here. So f of 6 is equal to 8. And 8, as everyone knows, is greater than 6. So excellent. We have, oops. Do this in. So then the hypothesis for some k, f of k is greater than k. So the inductive step is that f of okay, so we start with the hypothesis, and then we do our inductive step. And for our inductive step, we need to look at f of k plus 1, and we need to see whether or not f of k plus 1 is actually bigger than k plus 1. So the problem that we run into here, and this is like a serious problem, our hypothesis doesn't say anything about k minus 1. So I assumed that this statement was true for some particular k. I said there's somewhere where this theorem is true, and in particular, it's true at 6. And so what I would like to do is say, okay, it's true at 6, and I'm going to go and use the hypothesis then to go show you how to use the fact that it's true at 6 to prove it's true at 7. And then use the fact that it's true at 7 to prove that it's true at 8, right? That's my general induction methodology, is to go step by step, 6 to 7, 7 to 8, 8 to 9, all the way out, like use k to prove something about k minus 1. But now I've got this problem because my formula here says something about f of k, but it also, my formula uses f of k minus 1. So I know that f of k plus 1 is greater than k plus f of k minus 1, but I can't simplify this, can't simplify any further because I don't know anything about f of k minus 1. So this is a problem. And the way that I'm going to deal with this problem is I'm going to change my hypothesis. So the type of induction we've been doing, so the induction that we have been doing is often called weak induction. We weakly assume only that the theorem, the claim, is true for k. But here we need to assume more. We need to assume not only that it's true about k, but we also need to show that this is true about k minus 1. So what I want to introduce to you is just to expose you to the notion of strong induction, which is the idea behind strong induction is to assume that the claim is true everywhere. So for weak induction, we are assuming that the claim is true for some particular k. For strong induction, we are assuming that the claim is true for everywhere before k. So my strong hypothesis, let's go repeat this. So let's now do, let's grab this proof again. This is now like a strong hypothesis is for all, let's say k, for all, what do I want to call this? Okay, so what I'm assuming here is I'm assuming that f of f of 6 is greater than 6, f of 7 is greater than 7, ... f of k is greater than k. So I'm assuming now not just one formula, but I'm assuming that these formulas are true everywhere up to k. And I want to say, so again, this is like using the ladder analogy. When we were talking about the induction ladder, weak induction is like, if I have a firm place to stand, I can always go one step up. Here we're assuming that all of the steps work all the way up to k. And if all of the steps work up to k, then I'm going to prove k plus 1 using all of the steps below me. So the again, the difference between weak induction and strong induction, it doesn't come up a lot. This is like, it's probably not the most important concept that we've covered in this class, but I just wanted to make sure that you had heard the terminology weak induction and strong induction. And whenever you are trying to prove an inductive proof, that makes use of like two different previous facts. So here we need a previous fact about K, and we also need a previous fact about K minus 1 in order to prove this theorem. The other thing is, because we need two previous facts in order to prove this, then I also need two base cases. What is F7? F7 is 13, which is indeed greater than 7. So because I use two previous terms, I'm going to need two base cases here. So then, again, once I make this strong hypothesis, doing the inductive step is actually pretty easy here. This is not a hard theorem to prove. So f of k plus 1 is, so f of k is bigger than k, and f of k minus 1 is bigger than k minus 1. So f of k plus 1 must be bigger than this. Because I've gone and all I've done here is I've replaced two Fibonacci numbers with regular numbers that are smaller than the Fibonacci numbers. So this is just using the assumption that I made about f of k minus 1 greater than k minus 1. And also, k is bigger than 5. So k is bigger than 5, which means that k minus 1 is bigger than 4. So then f of k plus 1 must be bigger than k plus 4, and k plus 4 is bigger than k plus 1. So now this is the claim is true for the k plus first Fibonacci number. Okay, any questions in chat? Maybe there's lots of questions in chat. Okay. So this is, let me, okay. Yeah. Saloni, strong induction is, strong induction is assuming you assume about two terms in order two or more terms in order to prove about the one next term. So I'm still only proving one fact, but in order to prove one fact, I need to use knowledge of two or more previous things. So that's the only conceptual difference here, is that here I'm using knowledge of two previous things. I'm using knowledge of f of k must be big, and f of k minus 1 is also big. And so I need both of these facts in order to prove that f of k plus 1 is bigger than k plus 1. Okay. So again, don't hesitate. If you have any questions, don't hesitate to type them in chat. I appreciate that the TAs are watching chat. So this was the first example that I wanted to do, and there's going to be one strong induction question on the homework assignment that is somewhat similar to this. How do I insert a page break? And I will, of course, share these notes that I've been making with you after this class. So there was just one more example that I wanted to do, and then I'm happy to let people work on the homework, or if there's anything that isn't clear on the homework, I can answer any clarifying questions, or like I or the TA can point you in the right direction. So the next thing I wanted to talk about was proving theorems about recursive programs, and it would help if I could spell recursive correctly. So here's an interesting program. So this program is the add5 program, takes in a number num, and let's see. So if num is equal to, if num is equal to 0, then I'm going to return 5. And else answer equals add 5 to number and return. Okay. So here's a program. Let's not capitalize things. I really need to be able to turn off on Google Docs my capitalization. But here's a function. So add 5 of 0 is returns 5. Right, if you give this an input of 0, it's just going to return 5. And then similarly, if we go and take add 5 of 1, add 5 of 1 returns 1 plus add 5 of 4. No. Add 5. Okay, right, here's what happens. Add 5, if you give it an input of 1, it's going to add 1 to whatever the previous add 5 is. So when you call this function with an input of 1, it goes and runs the function on 0, and it's going to get then a, right, if you run this function on 0, you get a 5. So this is going to be, which is 1 plus 5 equals 6. Similarly, add 5 of 2 returns 1 plus add 5 of 1, which is 1 plus 6 is 7. So this is a recursive function. It is a function that calls itself repeatedly. In order to figure out add 5 of 3, I would call add 5 of 2, which calls add 5 of 1, which calls add 5 of 0, which returns 5, and then we just keep adding 1 repeatedly. So let me just go and check the, okay. Yes. Okay. Yeah, so Harley points out that this is a function that would be easier to write in a non-recursive fashion. So I could write a function like simpler. Returns 5 plus num, right? So claim both of these functions produce the same result. Okay. So what I'm this is like a wasteful use of recursion. If somebody gives me this recursive function, I would like to go and do something simpler. But in general, and again, maybe this is a trivial case, and so maybe in this case you can figure it out without doing a proof. But in general, if I want to replace a slow, complicated function with a simple, fast, efficient function, I want to make sure that they're actually producing the same answer. That is, it is bad if I'm like on some mission critical code for, you know, say space shuttle launches, and I want to make the code more efficient, and so I go and simplify it. Before I go and check in this code and give it to my teammates, I had better be pretty darn certain that my simplification of it didn't actually break things and cause it to sometimes return different values. So basically what I'm interested in here is I'm interested in proving that the that add 5 always returns 5 plus none, add 5 of. And of course, as has been the theme for the last couple weeks, the way that I would prove this is through induction. So let's prove with induction. Let's grab me a different color here just to set this off. We will, so we start with a base case, and our base case here is really simple. It's just num equals 0, then add 5 of 0 returns 0, or no, returns 5. So how do we know that add 5 of 0 returns 5? Well, we step through the code and the if statement triggers, right? So this causes this makes the if statement true, so then it's easy to see that this returns 5. Okay. Inductive hypothesis. Hypothesis. The inductive hypothesis is we will assume that add 5 of k returns k for some k greater than 0, and then our inductive step is we want to, doesn't return k, it returns k plus 5. And our inductive step is to prove that the claim is true for add 5 of k plus 1. So in this case, again, I think this is relatively easy to see that in the case that you have k plus 1, right? So k plus 1 is not 0. Let me go and bring this down. K plus 1 is not 0. So the else part happens. The if is false. So what happens in the else part? So answer gets add 5 of num minus 1. So answer equals add 5 of k plus 1 minus 1, which is add 5 of k, which is, by our hypothesis, we know that add 5 of k is just k plus 5. Again, this is a super simple example, but I think it shows the idea for like proving a simplification theorem about a Python function. So then add 5 of k plus 1 returns 1 plus answer, which is 1 plus k, claim is true. Victory. And so lo and behold, we have that this function always returns the number plus 5, which means that you could go and simplify it and you would make it faster without going and changing any behavior. So let me check my messages. Okay. Wonderful. So then let's prove it with induction. Yes. So then the final example that I wanted to go to before we can move to the homework is a similar but slightly more complicated example, which is, let's just go and insert a horizontal line here. So what if instead of add 5, we had so this is now a more complicated function. It has two inputs, num and x. So add of 0 and 5 returns 5. Add of 0 and 18 returns 18, right? So add of 0 and x returns x, right? Because if the first input is 0, then it's always going to return the second input, which is x. So add 0, 5 is 5, 0, 18 is 18, 0, x is x. Similarly, if we add 1, 5 is going to return 1 plus add 0, 5, which is 1 plus 5 equals 6. Similarly, if we add 1 and 18, this returns 1 plus add 0, 18, which is 1 plus 18, which is 19. So if we add 1 and 18, we get 19. Similarly, if we add 1 and x, that's going to return 1 plus add 0 of x, which is 1 plus x. So this function, add 1, 5, like this is just the plus function. It's a weird recursive way of writing the plus function in Python. So my claim is that add nx always returns n plus x. Right? So, and this is a little bit less obvious than the last one because this is a more complicated function. But exactly the same methodology works to prove that we could simplify this with, let's go and So my claim to you is that these two functions always produce the same result. That you can add an x, which is this weird recursive function, and that's just the same as saying n plus x. So how do I do that? I'm going to just grab my induction proof from up above and edit it. So first of all, we need a base case. So if num is equal to 0, then right? So if num is equal to 0, then this is if statement is going to trigger. And when the if statement triggers, this is going to return just the second input x, whatever it is. So that's my base case. Now I'm going to assume that for some so I'm going to assume that for some k, that this addition function will, if you give it k and x, it's going to return k plus x. Like there's some particular k where this works. Starts out with 0, right? Like first of all, we say, okay, this works for, and this is true for all x. So now the inductive step, we're interested in now adding k plus 1 to x. So k plus 1 is not 0, which means that the else part happens. Right, here's our, again, we have this if the first input is 0. So in this case, num is k plus 1. We know that k plus 1 is not 0, so it's going to return x. Wonderful. So then answer is going to be, which is add. So the add function for k of x is just k plus x, because that's exactly what our hypothesis was right here. And so, boom. So then what does our function return? So we go and we go here and we compute our ANS answer. The answer is just adding the previous number to x and then adding 1. So let's say add, so then this returns 1 plus answer, which is 1 plus answer is 1 plus k plus x, right? This is answer is k plus x, so 1 plus answer is 1 plus k plus x, which is exactly what we wanted. That k plus 1 added to x is x plus k plus 1, so this is exactly what we wanted. And I have a typo up here, which I will fix. Okay. So anyway, I just wanted to provide an example. We've done previously proofs about, let's see. So we've done previously proofs about loops. And so I just also wanted to show you explicitly like a proof about a recursive function. And you'll have one of these to do on the homework assignment. Sorry if you're having technical problems. I'm going to try to record this, or I think I am recording this. So hopefully you should be able to get the video, even if it's not, even if you're having technical difficulties right at the moment. But otherwise, I guess, are there any questions about these examples? Does anyone have any questions about these examples? Okay. Then the next thing is, why doesn't everyone go and take a look at the homework? So if you go on Canvas, you should be able to find the homework. And the homework assignment is several problems that you've already seen, and then a couple problems that are more similar to what we did today. So I would like you to, look at the homework and let me know, do you have any questions about, like, do any of the problems not make sense, or do you need help being pointed in the right direction on any of the problems? So I'm just going to sit in the stream for a while. I think I'm going to go turn off the recording now. And